All right, folks, in this play posit, we will see how we actually apply the connected objects technique to solve a problem. So please copy this to your notebook. And those, excuse me, those numbers are a little bit hard to see, but you have 2.7 kilogram block, connected to a 1.6 kilogram block, and there is friction on the table. So now that there's more than one object in the system, you have got to have subscripts on your weight vectors because everything has a weight. So you can call that W1 or you can say M1G. And then we have either W2 or M2G. And I know you all know how to calculate this. So that's 26.5 newtons and that is 15.68 newtons. Sorry, 15.68. And so they both have weight. This one's touching a surface, so you now have a normal force. You don't really need a subscript on the normal here because there's only one. This is a boring problem where these two are equal. You've done enough problems where you don't have to show me that the sum of the vertical forces add to 0. You can just say this is a boring problem. That normal is clearly 15.68. You have two tensions, but they're the same because the rope distributes the tension. So it's pulling, the center of the rope is here, the rope molecules are stretched and they're wanting to pull back. So they're both pointing towards the center of the rope, and these two forces are equal to each other, even though I made that one shorter. And then the final force is friction on this guy, and in the miscellaneous column, friction equals mu n, so 0.106 times this normal, which is equal to the weight, gives you 1.66 newtons of friction. Okay, so far nothing new. All of the forces are forces you've seen before. The trick is, the way some textbooks teach this is you would do F equals ma for this object, F equals ma for this object, and then you'll have two equations and two unknowns. You don't know the tension. You see, we've actually determined every other force in this diagram. You don't know the tension, and you don't know the acceleration. Oh, and then I highly recommend, this is accelerating down. So we can talk about this in class if people want to, but even though I spent so much time saying, hey, just be really consistent, to the right is positive, up is positive, what a pulley does for you is it kind of rotates the axis system as you go around the pulley. So the new rule is that with any force with the acceleration is positive, any force opposite the acceleration is negative. And again, please bring this up in class if you don't like it, but otherwise, if you really wanted to make up positive for this block, then these two objects wouldn't have the same acceleration than the object of the top block. They would have negative the accelerations of each other, and then you would end up with two equations, two unknowns. It's just annoying. Okay, so again, reach out if we need to talk about this in class, but I highly recommend you draw the acceleration vectors on your diagram, and then that helps you define positive and negative. Okay, so we drew the force diagram. Now we're going to find the acceleration of the system. Both objects have the same acceleration, right? If they didn't, then the rope would stretch out. Like if this was accelerating faster than the block on the table, the rope would be stretching out, right? And that it is possible, but we're just saying it's not happening. Okay, so what goes in the numerator is only the forces parallel to the motion and external. What goes in the denominator is easy. It's just the sum of all the masses. Okay, so what I recommend that you do, not mandatory, but if you have a highlighter, highlight the motion, and then any force that is going with, let me see if this works, any force going with the motion is positive. So let's see how that works out here. So you see how any force that you kind of trapped in that motion is important. You see how the normal and the weight were not kind of trapped by the highlighter? They're perpendicular to the motion, so they can't affect the motion. So that's knocking, even though the normal is external, not going to go in the numerator. Even though the weight is external, not going to go in the numerator because they're not parallel to the motion. Okay, so let's look at what we have. We have this weight that is with the motion, so that's positive. So we have 26.5 newtons. We have this tension that is opposite the motion, so that's negative. Working our way around, oh, we have this tension that is with the motion, so that's positive. Normal and weight perpendicular, so don't count them, minus friction, and then all of that is over 1.6 plus 2.7 kilograms. Okay, so I like to do this only once. Clearly, we don't want to keep doing plus tension, minus tension. Those are going to cancel. That's why we're not counting them. Internal forces will cancel. We are only going to count the external forces. That tension was between these body A and body B were both in the system, so that's always going to cancel. Let's not count it in the first place. All right, so our numerator is 26.5 newtons minus friction, which we already calculated, all over 4.3 kilograms. If you do out the math, you get 5.78 meters per second squared. All right, one way to check your work is that this system of two objects is powered by gravity, right? So that should be less than 9.8. There's no way that can be more than 9.8 if it's powered by gravity. Now, if you had a fan cart or a rocket, or, if you have other outside forces, absolutely you could have something accelerate faster than 9.8. But you can think of that as, if you cut this rope, this 2.7 kilogram wants to accelerate at 9.8. But it's not just accelerating itself, it's got to accelerate the other object, whose weight is not helping, and it's got to fight friction, right? So that's slowing it down from 9.8. The other way to check your work before we do the tension part is this tension's 26.5. Sorry, this weight is 26.5. Oh, we haven't found the tension yet. Never mind. Okay, so check your work less than 9.8. All right, so we found the acceleration, but now we need to find the tension. If we look at both objects together, tension's an internal force, it will always cancel, so we can't figure out what it is. So in order to find the tension, you need to isolate either object. It doesn't matter which one. So it's kind of like when we did the collision problems, you can plug the time back into either object's position function and that'll work. And then you can check your work by looking at both. Let's look at the falling block. So now we're going to just look at that object. You can define anything as your system. We are defining this as our system. And now tension is an external force because it's coming from that object, which is no longer in our system. Okay, I would suggest we still keep the same sign convention, but if you wanted to now, since we're just looking at this, call up positive, that would be okay, but then your acceleration value, excuse me, is negative. So I would suggest, since we already have this on the diagram, let's just continue to call down positive. All right, so we have the weight of this block, which we already calculated was 26.5. I erased it. Minus the tension, and that's what we care about now, equals M, but now the M is just the 2.7. That's the only thing in our system. And then A was positive 5.78 because we defined down as positive. Okay, so 26.5 minus This ends up being 15.06 equals tension. So I brought that over to that side, and I brought this over to that side. So tension equals 10.9 newtons. All right, so you can check your work if you want. This weight, excuse me, was 26.9. 26.9 better be bigger than the tension because it's accelerating down, right? So 26.9 is bigger than 10.9. This tension is also 10.9. 10.9 better be bigger than friction, which was 1.66. Okay, so you can check your work that the forces, you know, the net force must be in the direction of motion. Okay, and then I realized there was one more thing I wanted to warn people about super quickly, and then we're done. When you do some of the forces of the whole system, parallel and external, over the sum of the masses, sometimes you'll be subtracting things up top. This denominator is always plus. Mass does not have direction. So even when we do problems where you're subtracting both of the weights, sometimes people then get confused and subtract the masses. Inertia is just going to slow you down, so you keep on adding it up. And then you can do this yourself if you want. I'm not going to make the video any longer. You could do sigma F equals ma, just focusing on the 1.6, and say tension minus friction equals that mass times A, and it's a great way to check your work. You'll get 10.9 looking at the top mass as well. All right. Hope that all made sense to you. And as always, see you in class, and thanks for listening.